Oh, what's up, everybody? Welcome back. Today, we are working on implementing large-ish matrix multiplications with OpenCL for the purpose of training a neural network to scan barcodes for us. Okay, sorry. That was a lot. I had to be careful about the words that I chose there. Okay. So, we are working on a neural network. Our neural network needs to scan barcodes, and of course, we have an extreme terminal case of not invented here syndrome, so we have to build the whole training framework from scratch. GPUs, pretty cool, pretty fast, and I like the idea of using the speed if we can get it. Doing this training on CPU, I imagine would take a while, like, maybe it wouldn't because the problem's simple enough, but I just like the idea of doing it on GPU. So let's do that because that's what all the real guys do. That's what all the real people do in this world. Where we're at right now, we have trained on CPU a pretty basic neural network. He takes in A and B, and he outputs 1 if A is bigger and 0 if B is bigger. Wow! This involves, a couple multiplies and a couple weights. So we have like weight here, we have weight here. This, we get like A W1 times B W2. We throw this shit through like an activation function, sigmoid. And then we calculate like how wrong was this output. We back propagate where we say like, what is the derivative of sigmoid? What is the derivative of like A or W1 with respect to A? What is the derivative of how, I don't know the words here, so we will say, how would I adjust W to make the answer less wrong? How would I adjust weight 2 to make sure that the answer is less wrong? So we've kind of got this, and we want to upgrade to being able to do this on GPU. So the idea here is that we would maybe do like, we would take like, 100,000 A's and 100,000 B's, and run them all through the network at once, calculate how wrong this was all at once, and then do back propagation, figure out how to adjust the weights all at once. That's kind of like the goal we're working towards. We have started with the idea of give me a list of numbers. 1, 2, 3, 4, 5, 6. And on GPU, could you sum them all, right? Now, this is an important part of matrix multiplication. So when we get into like bigger neural networks, we might have something like, give me a list of like 1,000 numbers here and another list of like 500 numbers. This is 1,000, pretend that's 1,000, pretend this is 500. And for each of these 500 numbers, could we do like multiply adds with all of these? Which means that this is going to end up being like, we're going to put all of these like multipliers in a box of 1,000 wide by 500 tall. And we're going to take 1,000 numbers here, right? 1,000 numbers here, and do matrix multiplication, which means that we're going to have, as we do matrix multiplication, we're going to end up with 500 rows of 1,000 elements to sum together. Partial derivative of loss with respect to the weight in question, I think, is the technical term that I was looking for. Yes, something like that. So the idea of being able to say, I have, 10,000 numbers and I want to sum them in chunks of 1,000, right? So like every 1,000, sum them all on GPU is like a thing that we might want to do. Last stream, we implemented like the first piece of this, where the problem is not like as simple as one might think, right? If you've never thought about like parallel programming before, which I haven't really, you would think, I'm just going to do A plus B plus C plus D like I would on CPU, right? You make a loop for 1 to 1,000, add, hype. But that's like kind of like a CPU version of the problem. On GPUs, you kind of have like a fuck ton of kind of slow guys, and they can all do work at the same time. So a better way to do it on GPU is to find a way to like do this sum in parallel. So what we did is we said, I have A, B, C, D. Let me sum A and B together. Let me sum C and D together. And then like you kind of like walk this tree where you keep going down and down and down until you have like one number left. That's fine and dandy. Except for the fact that GPUs, while they are heavily parallel, the parallelism is like kind of limited in some ways. Limited is maybe the wrong word, but like architected, I guess we should say. So if I have, a million numbers, so many numbers to sum, right? The way this works is that you say to the GPU framework, in our world, this is OpenCL, we say, hey, how many things can you kind of do in one group? And he'll say like 256 is what he's saying to us right now. And so we need to kind of do this million. We can do 256 operations at once, which means that we can actually sum 512 numbers, because each core in this 256 block will look at like two numbers, right? So we can sum 512 at once. So we need to like break this up into chunks of 512 and then like recursively sum those. Because within this like 256 block, we actually have some like really fast memory. So there's kind of like global memory over here somewhere. This is kind of like accessible to everything in the GPU, but it's like kind of slow because it has to be really big, right? When you say I have like, my GPU comes in a box that says it has like 24 gigs of VRAM, like this is kind of what it's talking about. But in like the same world where on CPU you have like L1 cache, L2 cache, and then like DRAM, right? This is kind of like your DRAM of GPU. When you like run these like blocks of 256 calculations, these, as far as I understand, end up on like a streaming multiprocessor, they call it. And in here, you have like L1 cache. So you have like chunks of memory that like only people within the block can access. And so that's why we have these like broken up this way, right? If you worked directly on global memory, you could do it all at once. You'd be totally happy. But because you want to leverage this like fast fucking RAM, then you want to do this in small chunks. So that's kind of hand wavy how we got to where we got. And so I guess what I want to do today is extend this to work on numbers that are big enough, and then hook this up to matrix multiplication, and then maybe we'll see if we can like implement the rest of like neural network training. We'll see. Okay, so that's the plan. So let's look at what we did yesterday and try to work our way forwards. So the way this works, we have sum.cl, OpenCL file. This guy has a function sum that runs, for each piece of data. Okay. And he says I have some local ID, i.e. like which index into this like chunk of 256 guys am I, as well as my global ID, which is like which numbers am I working on, essentially. And all we have to do here is we do like an initial sum with our neighbor. So we say, given like the big list of numbers, given my big list of numbers, I kind of sum like this. And then within here, then he kind of loops in his like block of 256 numbers, and he kind of like does sums like this, hand wavy, because that way he doesn't have to worry about like coordinating memory, if that makes sense. Do you need to call GPU calc 1 million over 512 times, squish 1 million to 500k? I think it's like log 2 of 1 million, I think, over 512. I think it's log 2 5 like 1m over 512, I think. But what I realized this morning when I was thinking about this problem, is if we can get up to 512 numbers right now, what are the chances that we have like a fully connected layer? Like, what is like our max input size? Let's think about that a little bit. So say we're doing barcode scanning, and we do, we work on some like relatively high res image, and we're looking for a barcode in this thing. This is gonna be like maybe like a 1080p image, right? And we're probably going to like do a bunch of convolutions that will kind of like shrink this guy down and down and down into some sort of like hand wavy. Barcode's probably going to take up like What? Like, I'm gonna be pointing my camera at it. We actually have some sample pictures. Hold on. We have some sample pictures, so let's look at those. Mayo scan, I think we called it in here. Mayo here, maybe. Mayo scan. So, like, this is maybe an example of an image that we might look at. So, this is probably like what? Like 1/8? Maybe we get a little smaller, 1/12, right? So let's say that we have, eventually this makes it down maybe to like a 12 by 12 thing with some depth to it, right? So like how many features do we care about for each pixel in this 12 by 12 space is like a thing that we might have, right? So kind of hand wavy, say we want to look at like all of that information at once, okay? So that's like kind of like on the order of 12 by 12 by something. So let's say this is like 128, right? Maybe there's like 128 things we care about in each pixel. So 12 by 12 by 128 is probably pretty big. 12 by 12 by 128. Yeah, that's pretty big. Okay. So I was going to say that if this number was like 1,000 or like 4,000, we might be able to get away with the idea of just using float 4s here everywhere. Because if we just change this float to float 4, we quadruple the amount of space that we could do in one shot, which would be 2048. But this number is much too big for that. Much too big for that. Okay, cool. So we're back to the idea of trying to make it so that we basically recursively call this thing and keep shrinking the numbers down. So we have some tests here somewhere. And these things work. Since you keep intermediate data in fast cache, you need to make sure that does not go away. But if you need to schedule so many groups that they cannot get their own cache, is the GPU smart enough to deschedule threads? Pretty sure yes, and swap the cache out to VRAM, much less sure. That's a good question. I was under the impression that thread blocks get like pinned to multiprocessors, but I'm not sure. That was my impression that I got when Googling this earlier, but it was very like, my knowledge on this is very shaky. Okay, so far we've been able to get to the point where we have like correct output for anything that is smaller or equal to the size of a batch times 2. So if we change this to be a size of a batch times 2 plus 1, I believe this starts falling over, right? And we should start trying to figure out why. So we're hoping that we can kind of like chunk this stuff up in a way where if we have, say we have batches of 512, right? Our local size is 256. Each thing can process 512 numbers at a time. And so we're saying local size times 2 plus 1. So we should have 513 numbers here, right? So that kind of gets allocated into our guy like this, right? So the first chunk looks at the first 512 numbers, and the next chunk looks at one number. And what we want here is for this stuff to kind of output into 2 numbers in the global output, right? The sum of the first 512 and the second one, right? We want 2 outputs for this thing. Okay, so I think there's like group ID here. I think that's a thing that exists. And I think that this tells us essentially like 0 here, 1 here. And if we had like, more groups where it was like, the first 512, the second 512, and then like the remaining like 200, right? I think this would get like group 0, 1, 2. And so I guess the question here is how do we just like basically set this thing up so that in group 2 we get 200 somewhere, and in group 0 and 1 we get 512 somewhere. So I think this goes into like our reduce iterator. So this guy's job is basically to say like, keep having keep having the input space, right? So he says like once we have taken our like 512 numbers and put him in our 256 wide buffer of numbers to sum, 256 wide local memory, his job is basically to keep having, he keeps track of like how many elements are left in this array, right? So maybe we only had like, you know, maybe we started with like 150, right? Numbers in this thing. We didn't use the whole area. So this guy like basically keeps track of going down to from 150 to 75 after one iteration. Then from 75, having this, we actually need to go half plus one, or like round up half. So that's, see, he just like keeps going down until we get down to like one element left. His job is just basically to keeping track of like which threads are allowed to execute on this data still. And he outputs like the pair of, you know, if at the partition of 75, he outputs the pair of like 0 and 75, 1 and 76, etc. He says like, where's my other guy coming from? So I think all we have to do here is change our like initial size that's like remaining in this chunk to be limited based off the group ID. Okay, so we have total number of elements. We have how the size of our batch. So maybe calling this like this. So this is like that 512 here. So if we are in group 0, say we have exactly 512 numbers. N here is 512. And group ID is 0. Okay. So I think it's like, we only want to behave differently on the last batch. Or I guess, so we can't just do like modulo here, I think, because like we can't just do like percent batch size, because that would mean that if we had 512 elements, this would be 0. So it's like group ID times batch size is probably useful in some way. So this would give us 0 here, 1 here, or 0, 512, 1024. And then I think it's like, if num elms is greater than the next one of these, we do one thing. Greater than or equal to. Then we just use the batch size. Right? Because that means that like we're in one of these. So we just use the batch size. Yes. Else, we use num elms percent batch size. So if num elms is 512 and batch size is 512, then this is 512 is greater than or equal to 1 times 512, which is true. This returns 512. Otherwise, num elms is 513. This is 512. Then we go to this case and get 1 back. Yeah, that seems right. And then I guess this is C, so we say like initial size is, we put this condition like this. Batch size, else num elms percent batch size. I think that's right. And there might be some math way to do this without the if condition, but I guess kind of fuck it. And then here on our output, I think we output to get group ID. Or I guess just group ID like this. And what we should see if everything works here is we should see two outputs that should sum to the expected value. So they're expecting this guy. Can we do this plus this? 131328, 131328, that might be right. Okay, sick. Sick. Okay, so we now have a thing that will output to, he will like fold down as much as he fucking can and then output a list of numbers that need to be summed again. Okay. Okay, that's useful. So we have to figure out, I guess our abstraction here in CPU side needs to like know that he has to call it multiple times. I believe. And if we were to call this many times, I guess we should probably double buffer, right? So like the first output goes to some smaller buffer, and then this guy can just reuse this guy, and they can kind of ping pong back and forth until they're done. Okay. And the size of this first buffer is, you know, in over 512, but like rounded up. Right? Yeah, because but 512 is like dynamically determined because it depends on the GPU. So it's like, while true, okay, so we have like out 1 and out 2. That these guys both have to be read write actually, because we're double buffering. And the size of out 1 is, you know, like seal div local size 512. Yeah, and then out 2 is another seal div of that. Nice haircut, looks nice. Thanks, man. Appreciate, that's nice of you to say. I don't really like I struggle with people like talking about something that I'm like, I don't know, man, I don't really care. But it is not, you are trying to say a nice thing, and so I should treat it like you're saying a nice thing. Okay. We've implemented this once. What do you tell the barber to get that cut? I don't tell him anything. I just take out the razor and do it with my eyes closed. He says, just fuck me up, fam. Okay, rude. So maybe doing this final sum on CPU would be faster and simpler. Yes, but this is going to turn into something. The final output of this is we're actually summing a bunch of lists of numbers, right? So we're taking like a bunch of numbers this way and summing them like this, you know? We're doing like this sum sideways to fold this into like however many rows there were here. And so like the final implementation of this, I think, should live on GPU almost entirely. You know what I mean? He's eyes closed. I was like, okay, fuck you. Haircut looks whack. Thank you. There we go. Okay, so yeah, this is eventually going to turn into this, which is why we're doing all GPU. Okay. Local size, here, we need seal div. So, you know, iter1 out is seal div local size by 2, and iter2, I guess we'll call this iter1 size, and iter2 size is iter1 size by 2 again. And these guys are probably U sizes. What is the output of this? Yeah. Okay. So we implemented this on the GPU side. It's going to be the same fucking formula. It's this. Numerator plus I guess denominator. Denominator minus 1 over denominator. Okay. We should probably test this. So we're like 10 over 3 should be 4. 9 over 3 should be 3, and CL div 1 out of 3 should be 1. Cool. Okay. So here we have iter 1 size like this. We have iter 2 size. And we say, well, true. I guess we have like our out. I guess we kind of want like out, out buffs is probably like the 2 of these guys. And out index is 0, right? And while true, we do this stuff. I don't know. We set up our kernel arguments. So probably most, I guess A and B are going to change. Local memory size is going to stay the same. Size is going to change. And log will stay the same. Okay. So buffer is going to be A initially, right? So we say this is in buff. We have this is out buff set out index. And size is like remaining size, right? Okay. So this is wrong. This should come from size, not local size. Okay. And so then we just say like remaining size is equal to ceil div remaining size over 512. So this 512 should live somewhere. I don't know why I wrote 2 here. This should be 512. Oh, batch size here is local size times 2. That's where this comes from. Right, and then we use batch size everywhere. Boom, boom, boom. Figured it out. We got there. Out index plus equals 1. Or equals out index plus 1. Percent out buffs. Len? In buff is equal to out buffs at out index before we increment. And I don't think there's anything else you have to update here. Looking at what Gemini spit out for reduced sum in OpenCL and seeing what online feels like, there should be an easier way to do this kernel, lol. Are you saying that what I did is fucking stupid and like the implementations are simple? Because it could be. I was kind of down to like run it myself and then figure it out from there. I kind of like the idea of not looking until later, you know? What the fuck am I looking at here? Oh, I see. This is iter 1. This is ceil div size by 2. There we go. And I guess we do have to run the kernel. That's true. So this is remaining size now. Remaining size. And then if remaining size is equal to 1, we break. To be honest, the first time we do GPU program, the highly parallel structure be super confusing. Yeah, it took me a really long time just to do like something really simple last stream. It just kind of like takes a minute. But it's okay. So this is like var ret is a floating point number, which is undefined. Then we read this into as bytes ret. Okay. And read buffer here. The length is determined from here, so I think we're chilling. Okay, I mean, there's like a chance that's right. Out index he doesn't like here for some reason. Let's see. Unable to resolve comp time. Ooh. These are buffers, I think. Oh, this needs to be const true. So true right now. And then seal div here needs like either here. Batch size here is fine. Okay, so let's run the test now and see if the existing ones pass. He's mad because reading back the buffer is failing. That's interesting. Can we look at... Can we just breakpoint here? Oh, I think I need to get... No, he's actually... Okay, interesting. We are getting here, right? Yeah, okay. And then can we just print a couple numbers? Oh, fuck. Fuck, 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 fuck. God damn it. It's in bytes. Okay, cool. All 4 tests pass. Wait, that's hype. That means this worked. That means this worked! So can we do, like, local size times 8 now? Does that work too? Woo! That's awesome, man. You love it when it just fucking works, man. That's so sick. Yeah, and so he is... We do see him, like, running, you know, global IDs like 768 and shit. So can we also... I would just like to confirm that this is kind of like... That we're not, like, fucking up our tests somehow. So I would like to just make sure... that we are iterating from, you know, this... Iterating to this. And then can we turn off logging here? Yeah, okay. Yeah, so here we do see examples of it having to iterate down to like, oh, I've got to, you know, do 4. So is it arbitrary size now? Runs with correct results from numbers 2 to 1,000,000? Yeah, it should, right? So if we just punch in like 1,000,000 here, we should see this you know, that's behaving as expected. Assuming that, like, this test is doing the right thing, which I think it is. Okay, cool. So I think that what I want to do now is, like, strided sum. It's a GPU, throw a trillion at it. We'll do a billion. How about that? A billion. Oh, wait. Out of memory. That makes sense. Oh, that's so funny. We're actually running out of memory, like, because we calculate it once on CPU side to check the answer. That's funny. Fuck it. It's fine. It's fine. Okay. So now what I want to do is I want to make it like strided. You know what I mean? So like be able to like sum subsets of the total. So the idea now is that I want to sum like a million numbers in batches of 1,000. So this is kind of like a i.e. like matrix of 1,000 by 1,000. Like we're like sum horizontally. Right? That's kind of what I want. So I guess it's like stride just comes in here. Okay, wait. Well, first actually, let's oopsies. Hit a little git commit just so we have somewhere to go back to. But stride here can be 32. So this is like number of elements, and this is the stride with which we are outputting, right? So then our exit condition is based off stride, not size most of the time, I think. So I think like I think this has to be 0, right? Stride has to be a multiple, size has to be a multiple of stride. I think. And so batch size is still the same. Our sizes for running the kernel. Okay, let's think about this. So we say we have width 513, right? Just out of the size that we can do in one batch. So this is going to be like, you know, this is going to come into 4 numbers, right? We're going to have like the first 512, like 512 from A, and then 1 from A, and then followed by 512 summed from B, and then 1 from B, right? So, and then we need to run this one more time to like fold these guys back, right? So we have like the idea of like iter1 size. Okay, so we have like output elements here is going to be size over stride, right? This is the number of things that we want to output. Each iteration is based off of stride, though. Not size anymore. Iter1 stride, iter2 stride, right? Our output sizes, though, are like output elements times iter1 stride, I think, right? So we're going to have like this many, right? So here, this example was that we have, how much was our input? 1026, right? Which means that we have 2 batches of 513 numbers. So then we have 2 times the output stride, yes. Okay, this makes sense so far. Then we still do double buffering. Our working size here is the same. Just, however many floats we can fit in local size. That makes sense. And what are our arguments here? So we have our input buffer is the total input. Yep. Output buffer is the output buffer. Yep, that's the same. And then remaining size here goes... We must still have a remaining size. This is how many elements... Like, this is, in this case, 1, 2, 3, 4. Which I think makes sense. We still need to execute over 4 things. But then I think we need a stride as well, right? It must be that our sum kernel takes in a stride here. So this becomes remaining stride. And I guess we just have to keep track of both. It must be, right? It must be. Okay. So then, as we kind of go down, we iterate by stride now. Okay, and then our exit condition is remaining stride is equal to 1. I think that's still true. Uh-huh. Then what? Then for now, I'm just gonna return these things on CPU, which isn't great, but that's fine. And then our remaining size here is output elements times the remaining stride. How many things do we have left? Yeah. In buff, we switch our input buffer, and our output, we switch our output buffer. Yeah, all of that's still the same. Now, our return value for now is going to be CPU side. And we're going to be like, output elements like this. And slice as bytes of ret like this. And then we return ret. Okay. So now, our existing shit is going to be broken. So I think we just huck a 1 in here, right? We just say stride is 1. No, list size. Yes. Then this guy gets like this. And then we return element 0 of this thing. Okay. And then everything should just work as it was. Yes, okay, so everything is working as it was, which is great. Okay, so now we just need to adjust our test to start doing strided output. So here we just kind of duplicate everything we were doing. Can we actually do this? Just throw nulls everywhere. Okay. Then it's stride is params 1 or else size. Yep. And then we pass in stride to whatever the fuck we're doing. So this guy gets stride here, and this gets passed along here. Expected. Whoa. Okay, and then now we need to adjust this guy to return a list of F-32s. Okay. Or we leave this the way it was, actually. We could leave this the way it was and have like a different function for many. Bow, bow. Wait, this is actually fine. This is fine. Okay. Expect approx equal abs. Now we need to change this to like, this needs to be like this. Calculation of strides here is annoying. So when we're outputting, we output now our expected values is gonna be a list of U sizes. Size over stride. And then as we're iterating this stuff, we have stride index is I over stride, like this. Expected U stride index plus equals 1, or plus equals the number. And then we iterate over expected, elements. And we test that the thing we got is that thing. Okay, there we go. I think this is getting close. So output is this, and then for each one we expect that, as floating point, float from int u is the same as output I. Yeah, something like this. Something like this. I think this does almost what I want. Something like this. Yeah, we're getting close. After you turn the barcode detector, you can also backprop input layer and make the network hallucinate barcodes on random images. Oh, that's sick. That's cool. I guess that's where that like initial DeepMind shit came from, huh? Back in the day. That's funny. Okay. Are we chilling? Almost. 71. Okay. That's not good. Our tests are no longer working. That's not good. Actual, 0. Not within expected tolerance of this. Okay. So, which of these are failing? I assume it's just like off rip, we're doing something stupid. Okay, cool. So his expected is some big ass fucking number, which means that we've done something fucking stupid here. So for 0 to 1, we have stride index is 1 over stride, which is maybe 1 here. Yeah. Oh, so this is 0 over stride, which is fine. So Then we get expected. Oh, we need to memset expected to 0 here. Okay, there we go. Doesn't sumless stride mean you sum each like space element versus consecutive? Well, we can define it to mean whatever we want. And we're defining it to mean this. An easy fix. An easy fix. Okay. So let's do, you know, so this is 1 million. So let's try to get 2 outputs of 500,000. And now this is probably not working correctly, which is reasonable because we haven't actually implemented this yet. All right, Jess, have a nice rest of your game off. Getting late over here. All right, night night. Nighty nighty. Okay, yeah, so this is just not doing what we expect now, which is reasonable. Which is reasonable. Super reasonable. So let us now go into some CL. And here we start looking at this stride variable. So whose job is this? This iterator. This iterator's job is to kind of like, let me think. Is it not this simple? No, it must be. So we're trying to go from 2 sets of 513 into 4. Right? 1026 to 4. So this first 512. Okay, can we start with a simpler case actually? 4, 2. 4 and 2. Simple, right? So here we have 1, 2, or I think it's 0, 1, 2, 3 is our initial input, which we're expecting to go to 1 and 5. Easy. Easy. So actually let's 6 and 3 I think will be easier for an initial attempt. So it's 0, 1, 2, 3, 4, 5. So this is supposed to end up as 0 and 1 sums with 2 in a local buffer. And then our iterator, which is supposed to like implement this reduction, needs to say, hey, I have I have 3 elements remaining per stride. And he also needs to know which stride is he in. Maybe not, because the strides are probably like kind of well defined based off of like I'm always going to be at like some local ID, which makes sense here. Is this I don't want to use the OpenCL stdlib stubbornness, or does the OpenCL not to provide? I don't know. I didn't look. Aren't you splitting up the strides by work groups and something like that? I think no. Because in this scenario where I have 6 numbers, like these are all within one work group. So I think it's just that like, I think somewhere we just need to huck a stride in here. I don't really know where, but it will become apparent, probably. Initial size here is probably where this comes in. So our batch size is this. Group ID is this. And I think that this, instead of being like the total number of elements, now is like stride based. Uh-huh. And then everything might just kind of work. Is num elements even used here? It actually might just be that we replace n with stride. So then because everything is in local buffers already. No, because this will only work on the first stride now. Yeah, so we definitely need like number of elements as well, because we need to cap that. So as we are dropping down, wherever the fuck this stuff was, 1, 2, 3, 4, 5, 6. So we should run if us plus stride is less than the total, I think. Should run. So before it was like if we are less than the remaining over 2. Okay. I think we're iterating by stride now. So remaining is like remaining stride size, let's call it. Which means that this kind of comes like this. Stride is greater than batch size, we use stride here. Okay? Then this is like if remaining stride size is less than or equal to 1, we return false. We have no more work to do. Otherwise, we seal div the remaining stride size. Everything is in stride space. Okay? Now, the only difference is whether or not this thing works. Now, it's only like the exit condition. I think this is also based off of the stride, actually. We just need to do, should run needs to take into account, like, total number of elements and stride, right? So, like, you know, if these guys, like, aren't really, like, in the array, then we need to know that we shouldn't run this, right? So it's like local ID percent stride is less than remaining stride size over 2. And local ID is less than total size or something. I feel it's like something like this. Yeah. This is how I feel like it should go. And then here we say stride and total size. I think. Then offset is still by stride, yep. Okay, and then this guy just needs stride here. Okay. So, good news is that I think all of the guys who aren't striding right now are still working, which means that we didn't like fuck everything up too heavily. How's stream going in general? Do you make enough money to avoid a full-time job? The bleeding is slow. But we are still bleeding. Okay, yeah, so all of the existing tests that aren't striding work, which is good. Now, 6 is not within the tolerance of expected 3. Okay, can we turn on logging for this? Let's just try to get a feel for what this guy's doing. So, this is bad, right? adding 9999 to 9999 means that something bad is happening. So we're getting like, is this the only thing we're logging on? Where is this coming from? I feel like that shouldn't be happening. Yeah. False, 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 false. Oh, here. There we go. Okay. So here we have, what does this mean? So this is logging when the iterator is returning that we should run. And so he is saying ID 3 is running and ID 0 is running, which, based off my understanding, is correct, right? Because we have 6 numbers, 1, 2, or it's actually 0, 1, 2, 3, 4, 5. So this is index 3, but index 3 has like garbage in it, is like what this is indicating, right? So why is that? It must be that this is broken. I mean, this is like our initial sum is broken here. It needs to be like add to my neighbor if he is within my stride. So if initial neighbor, I think it's like if initial neighbor percent stride is not equal to 0 and initial neighbor is less than n, I think. So if this is a valid number and he's not the end of a stride, then okay. But I don't think that's the bug. I just think that was a bug. Did I see that was adding 1 to 5? Should be adding 1 to 3, right? Okay, let's see. So this is adding, you might have. So this is adding 1 to 2 now. So that makes sense, right? So he kind of did this, 0 to 1 to 1, 2 get passed through to 2, and then he should be adding this. Then it should be 3 to 4 to 7. 7 should be added to 5 on the second one, which is not happening. We're seeing 9999999, which means that like initial index somehow, like n here is wrong somehow, maybe? But it can't be wrong. Initial index, this, and this. I don't think that this is wrong, but we should check. Yeah, so we do have n6 here. Oh, this is interesting. This is wrong now. Because we can't just do like pairwise adds, because the stride could be odd. Oh, fuck me. Look. So like before we had, you know, 0, 1, 2, 3, 4, 5. And we said like, you know, thread 0 is responsible for this. Thread 1 is responsible for this. Thread 2 is responsible for this. Right? For adding these two. This doesn't work anymore. Because like every once in a while we lose one. You know what I mean? Because now it's like now it's like with 0, 1, 2, 3, 4, 5, it's like 0 is responsible for this, 1 is responsible for this, 2 is responsible for this, 3 is responsible for this. And so is there like some sort of mathematical operation that we can do that will like truncate this? It feels like there might be, right? It's like you do like a ceil div of the stride by 2 times 2. Or you just do like, you know, something, I don't know what yet, is equal to like the stride plus stride percent 2. Right? So this increases the stride by 1 if it's odd. Then, so now this will be like, if we divide global ID by this will give us like 0, 1, 2, 3, right? Then we can do this plus global ID percent stride. This times stride plus this percent stride should now give us like the index. But that's not helpful. Wait, that's not helpful. It is helpful in some way. We're not quite there. We maybe like global ID over 2? No. So we want 0, 1, 2, right? We want 2 to end up here. So something is this 3, this comes up to 4 now. Something is 4. I don't know what something is here. It's like ceil stride, I guess. So 2 over global ID times 2 over 4 is 1. Okay, let's kind of like follow this a little further. 1, 2, 0, 1, 2, 3, 4, 5. Okay, hold on. Okay, we need colors. We need colors. So the data comes in as 0, 1, 2, 3, 4, 5, 6, 7, 8. Our IDs that we wanted to be associated with these numbers. 0, 1, 2, 3, 4, 5. Okay? Ceil stride is 4. Right? So, and our row indexes are 0, 1, and 2. Right? So we need some way to convert 4 into row 2. So this over 2, this divided by this over 2, right? So 4 over 2 is 2. Six over 2 is 3. Yes. So this is like this, which is just a ceil div. Half stride is ceil div stride by 2. Okay. So my global ID over half stride gives me this index times stride plus my ID percent stride. Should give me the right offset. Maybe over 2. Because now when I get to like 5 here, I want this to be 2 plus 2. So it's like this. I think. Okay. Lots of... Okay, how can we, like, possibly justify this? Okay. With stride of 3, we have data, 1, 2, 3, 4, 5, 6. We are trying to pair, some numbers with their neighbor if their neighbor is in the same stride. So global ID 0 gets 1, 2. 1 gets 3. 2 gets 4, 5. And 3 gets 6. Seal, like... Seal div stride by 2 in this scenario gives half stride is equal to 2. Global get row index by dividing global ID by half stride. Row 0, row 1. Okay. Yeah. So 2 and 3 get row 1. Yep. Now get data index by multiplying row by stride and adding... Okay, get data start. Yes. Like row start, I guess we can call this. And then initial index is equal to this. Okay. Now choose us by now we index into this row in chunks of 2. So I guess we want like row index. We might want this. I'm not sure. Then our data index. We want like a row offset is like this. Yes, I think. I think that's right. I think. I think. We are gonna have to do some printfs here. row call here. Row call data. There we go. What's he pissed about? Oh, these are make a float. All right, let's see. Um. Ah, fuck. Numbers at initial index. Okay. So, hello, why is this so big? Oh, because um we want this in here. Only look for valid numbers. Row 0, call 0, 0. Row 0, call 1, 2. Row 1, call 1, 0, 3. Row 1, call 1, 5. That feels really good, right? That feels really good. So that gave us this, 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 and this. That's really good. That's really, really, really fucking good. Okay. Now, we just have to fix this, right? So the idea that he is adding... So this should be 0 and 1 go to 1, and then we add in the 2. Then 3 and 4 go to 7, we add the 5. Now, he's adding 5 to 9999, so the second one is off. Which means... If local ID percent initial stride size, yep, is less than remaining stride size over 2, okay, and local ID is less than IT total size. Can we look at the temp buffer? Like, what's in here at this point? So yeah, we have 1, 2, 8, and 5. This feels wrong. Right? If we have 0, 1, 2, 3, 4, 5, this added like 3 to 5 somehow? Instead of 3 to 4? Okay, that's better. So 3 to 4 is 7, and then 5 to 5. Okay, so now this part's looking pretty good. Our initial seeding of the buffer. Now, it's just interesting that ID 3 here is looking at 5. So I guess our like temporary buffer at this point has 4 elements in it, right? It starts with 1, 2, 7, and 5. So I guess we want like 3 over 2 seal div for 2, right? Our chunks are... Ah. Our stride in the buffer, in our temporary buffer, is different. So we have stride percent batch size, so 3, right? This should still be 3. I think it's like this. Double up on initial stride size here instead of passing the original stride here. The original stride was 3. This is still 3. So that shouldn't make a difference. This is 3 no matter what. But I do think this is more correct. Shredder, thanks for the prime. Much appreciated. Is a silly question. Is there a reason what's hard-coded as clusters of 2 numbers add? Because we want to... I guess, like, technically you could make it bigger. Like, why couldn't each core do 3? Yeah, I don't know. It's just because 2 seemed most reasonable in my brain. But I guess you're right. There's no reason that we couldn't do, like, batches of 4 instead. Just because 2 seemed easiest. I kind of was thinking of it as, like, reducing should be doing 2 things at once. But, yeah, I think you're right. There's no reason it couldn't be 4. Okay, so this thing should be 3. Which means that this here should be like remaining stride size should be seal div 3 over 2, which should be 2. Okay, then we say, hey, we should run if our local ID over, mod 3 is 3 correct? No. This is like this. This is like a initial stride of data in like temporary buffer. Note different than stride of data. Okay, well, that's a lot better, right? So now we have 1, 2, 7, 5. We see adding 1 to 2, 7 to 5, and now it's just our should run condition is wrong now. So this total size is again size of initial temp buffer, not size of initial data, which is Jesus Christ. Which is what? So we have 6 elements. Stride 3. Which means we have 2 rows of... Yeah, it's like rows times seal div. So it's like rows is num elms over stride. Then we have like temp buff size is rows times seal div initial stride size 2. And so we have like row width is this. Temp buff width, temp buff height. Yeah. Wait, am I fucking stupid? Why is this batch size? This seems wrong. pretty sure this is wrong. Is batch size even used here? It has to be. So if we are in like the first... Oh, fuck me, dude. What if like the stride straddles a batch boundary? Which is very possible, right? Right? Like if we have strides of 3 and our batch is 256 numbers, 256 guys, like won't we want a stride that like straddles a batch boundary? That's not good. We can't handle that. Do we just pad the data to avoid this? Jesus Christ, everything's so hard. That's crazy. Dude, GPU programming is wild. Okay, how the fuck do we avoid that? Hold on. Okay. So either we have to prevent this from happening, right? Or we have to handle it. Those are our two options, right? So when we get into like the matrix multiplication case, I mean, can we just make it so that our strides are always... Okay. So I'm going to have some matrix. I'm going to be doing some matrix multiplication, right? Where I have 9 numbers in here, right? And I'm going to do this matrix multiplication, and I'm going to output a thing from here. And I guess like when we do our matrix multiplication, where we multiply these 9 numbers by these 9 numbers in our matrix, this is kind of where that like stride is coming from. The output of this thing, right? So these 9 numbers. And so I guess we could technically just pad this. And so we could just say like stride has to be a divisor of the batch size. We could say this, which would waste memory, right? Which I think is actually like one of the most constrained resources that we have. Like, you know, we really want to pack these GPUs as full of data as we can, is like in the ideal world. Right? So like this would mean this kind of like goes down if, how to say this? This is like less of a problem if the strides are large, right? And also, we get to pick this size. So we can also just make all of our layers powers of 2. Which kind of just solves everything, right? Yeah. Yeah, we can just say that. And that solves all sorts of problems, probably. Right? It also solves this problem that we were just dealing with, where like, where you know, all of this shit that we were just talking about, where like we can't handle this, just fuck it. Fuck it. We're in control of the data that goes into this thing. Yeah, fuck you, and everything that you want. Do we have assert in this language? Can we assert in OpenCL kernels? Asserts are not available. Okay, so what we can do is we can just assert this one level up though, right? Yeah. I guess like or stride is equal size. I guess technically we can handle that okay. Okay. Yeah, and then we can just like undo a bunch of this bullshit. Right, we can go back to initial index is global ID times 2, and initial neighbor is initial index plus 1. Fuck all this shit. I'm kind of down, dude. Okay. Okay, so then we come back in here. And now our problem is much simpler. I think. Yeah, because now we know that stride is evenly divisible. Okay? So total size is okay, initial stride size is initial stride of data in the temporary buffer, which is stride over 2. Okay? Which we do still have to seal div in case stride is equal to the number of elements, okay? We now know that our stride, our elements cannot straddle a buffer, or which is good. That solves that problem. But I think there's still something wrong here. This does not look right to me. So what are we doing here? We're looking at the remaining stride size. So the initial stride size is what we're putting in here, which if stride oh, this is like if stride is greater than our batch size, then we sum everything. Yeah, I guess that's true. Sure. I guess that's like kind of true. Then we don't need this stuff anymore? Okay, our assertions fail now because our test case was trying to use some bullshit. But we can just do 8 and 4 now. Okay. So I assume that if I comment this out, everything's happy. Okay. Now 8 and 4 is broken again. What's happening? He's adding 1 to 5, so we have it's 0, 1, 2, 3, 4, 5, 6, 7. This is our test case now. And so this is we're adding 1 to 5 and 9 to 13. So that's great. Now it's just should run is broken. So I guess we just need to print if log is greater than 0. Printf this stuff. Initial stride size is this. Remaining stride size is this. Local ID percent this. And total size this. Okay. Okay. And then I actually only want to log this if this passed. Because the majority of these will not pass. Okay. So local ID 4 passed. Initial stride 2. True. We have these 1, 2, 3, 4, like groups of 2 here. 1, 2, right? 2 is here. So that's right. Remaining, so total size 8. This is wrong because this buffer is size 4. So that total size needs to be seal div 2. Okay, that's looking pretty good. So then we added 1 to 5, 9 to 13, and so then we should end up with 2 values of, wait. Oh yeah, 1 to 5, so this goes to 6, and 9 to 13, this goes to 22, right? Yeah. Yeah. So can we print out the buffer that we get back from this guy now? What goes in here? Okay, so this 6 is correct. We see that here. Then the second value is wrong, probably because we're pulling from the wrong thing. We're always assuming that we're looking at temp 0, but that's not true anymore. So this is going to be like, we're going to have two values in here that are correct. So I think it's like if local ID is like percent stride over 2 is equal to 0, then we look at local ID here, right? So this stride is 4. Actually, seal div doesn't, yeah, it's fine, because sometimes it's big. Then 0, 1, 2, 3. So we want, yeah. Okay. I think that's right. Printf this outputs. Okay. That's not good. How did this change? This isn't even like the strided ones. This is the non-strided ones are breaking now. So how is that possible? Oh, because the output's wrong here now. Hold on. Okay. Now, I think there was still some fighting here too, but yeah. And I think no, we're not seeing any output here. Oh, because my bad. Log's not on in a lot of these cases. Okay, that's not good. But we should be seeing like 0 outputs to 0. Hmm. There's something here where our stride ID needs to like be smaller than the output size. Which is seal divs n by 512, I think. Yeah. Okay. So now we're back to this shit being a problem. So this is why it's breaking, is because on this iteration where we're trying to sum one number, it's literally just one number, somehow that's passing. I think. Oh, this is 3 numbers. Okay, so in the case where we have 3 numbers that we're summing, 0 outputs to 2 outputs to 0. That's not good. Maybe just percent stride. No. I think that will fix this, but I don't think it's right. Yeah, something's fucked there. Something's fucked there. I wonder if it's that, like, okay, so is it like my global ID? Hmm. So we have global ID for these 0, 1, 0, 0, 1, 1, 2, 2, 3, 3. Stride is 4. So my stride ID is global ID Over stride feels wrong. Over stride over 2. Okay. Then I guess, like, should output is equal to global ID percent seal div? Stride 2 is equal to 0? It must be. Yeah, it's this. So can we say, like, half stride offset or something is maybe what we want to call this? Yeah, it's like something like this. Fuck. Oh, oops. Percent here. Okay, that's a lot better. We got through a lot more. Now, I don't know which of these is failing. I assume it's this one, but... like, the actual strided... No, interesting. What did we break here? Bow, bow, bow. Okay. So this one? I see. 0 outputs to 0. What am I looking at here? So it's this one is failing. Can we see what's happening here? Okay. Interesting. So we have 513 elements. He's saying 0 outputs to 0 with double 513. What is a 0? Oh, because we're running this 2 iterations. I see. So I think we're missing the second output here. Yeah. So in the 513 element case, we sum the first 512 plus 1. So we should see somewhere that, like, 5... Yeah. So it's like, the problem here is that our stride is greater than our block size, right? Which means that, like, doing this stride ID check is not sufficient because we're, like, folding a stride into, like, multiple things. Right? It's like 5, 12, 1, 5, 12, 1, stride ID. You know, it's like, this is the first element of the stride, and we still need to output these, I guess? Which means that, like, whatever we had here before was kind of reasonable. It was like, get group ID 0 made sense here. Yeah, which means that the idea that, like, local ID equals 0 here also seems reasonable. But, like, then what is the other case here? It's because this output used to be, each block outputs to one element, right? But now it's like each block outputs to many elements, right? Because we might be strided within a block. which is the case we're in the failure case. So it's like output index is where many could be one. So we have like two output cases. We have one where like within a stride, we have to output many, right? That's case one. And case two is that within a block, we output many strides. Jesus Christ, it's so hard, man. It's so hard. So how do we determine which of these cases we're in? Bro. So there's the option where we're 513 wide. We have like 513 wide goes to, so we have like my brain, it hurts so much. It hurts so fucking much, dude. Okay, so if okay, we need to determine which case we're in. So if like stride is greater than block size, I think is like, oh fuck. Get local size. Okay, which we have. Okay, so if the stride is greater than the local size, we're literally just like, even this is not trivial, right? Because we can't just be like local ID is equal to 0. We can't do that because, like, say the stride is like this, but the block size is like this. You know what I mean? Like, how do we find if we are here? I guess there are two cases actually that we like, cases that we actually have to think about here. If stride equals n, then we have the special rule to do what we were doing before. Right? It's literally just this. Right? Just like if the stride is n, there's only one output. Right? Except for the fact that we have to fucking. Oh, wait, no, it's not that. It's not that. It's not that. It's not that. Because. Wait, yes. Yes, this is great. This is great. That's great. Otherwise, what happens? Here, we know the stride is a power of 2. Does that help us? No. We know that the stride is... What is our assertion here? That the stride is even. It's only that it's even! So it's like, ow! Ow, my head, man. So it's, okay, say we have, let's just bring it down. Bring it down to a simpler case. Block size, 4. We can handle 4 at once, let's pretend. Okay? Stride, 6. Okay? This means that each, no, I mean, this is just fucked. This is just fucked. Let's just change the rules. The stride has to be a multiple of the block size. Fuck it. That makes our lives easy, because then we can assume that we will always line up the beginning. Yeah, fuck it. Fuck it. And then it's just like, if local ID is equal to 0, it's the same. It's just, what is our output ID now? So, hold on. No, wait. Or that the stride is a multiple of the block size. Like, either way works fine. Right? It's like stride lining up with start because it's bigger or because it's smaller are both fine. You know what I mean? That seems reasonable. That seems reasonable. Okay, so then in this case, we just need to figure out this, I think, is still right. Maybe not. I think these are just different cases again. Stride is greater than output. If it's too big, it's the same, right? It's like output get group ID. I think. Yeah, I think these are the same. Otherwise, we assume stride is smaller than the local size. And in that case, it's output at stride ID. Then it's just this shit. So stride ID is this, output stride ID is this, and we need to check if local ID it's like local ID percent half stride offs and stride ID is less than output size. Did we just lose outsize? Yeah, sure. I'm like, quarter sold that this will work. Wait. I think we have some tests commented out. Let's not get too excited. Okay, so the old test passed, new test, where we have actual strided. Broken. Of course. Of course. But we're... Okay. 1 outputs 0 outputs 0, 4, 8. 1 outputs 0. Okay, so we just have to fix that. It's the stride ID. 1. That seems wrong. So our stride is 4. So we'll draw this back out. We had 0, 1, 2, 3, 4, 5, 6, 7. These guys go into temporary buffers in chunks of 2, right? So our temporary buffer looks like 1, 5, 9, 13. This stuff all folds left. So our temporary buffer indexes that should output are 0 and 2. Okay? So he's saying... So our stride here was 4. Oh, it's, oops, this is half stride is this guy. Stride ID is this over half stride, which feels maybe wrong, but I'll ignore that for now. This is, like this. And then is half stride off just gone? Yeah. Okay. Else if log skipped. Okay. So 2 skipped. 1, 4, 8. Okay. So we have local ID 2, stride ID 1, stride 4, and 8. So why is that wrong? So stride 4, half stride is 2. Local ID is 2%, half stride is 0. Okay. Then outsize must be wrong here. It's like... Here, stride is within the local size. So this is, yeah. How many strides are going? Let's go! Let's fucking go, dude! Holy shit, everything's so hard. But making things line up makes it so much easier. So now we should be able to be like, give me... a million things, stride 4. Out of memory, fine. Yeah, that's hype. That's hype! Yeah, okay, we're getting somewhere interesting. For sure. So I think, like, any... that works. 16 should work as well. Yeah. Yeah, that's hype. Okay. Jeez Louise, man. That's a 2-hour, 5-minute point, so I think this is, like, a good place to stop. But holy shit, it's actually, like, so much harder than... Like last stream, like I titled yesterday's stream, "Holy shit, GPU programming is good and weird," or hard and weird, sorry. And it's crazy that like it's even harder than I thought. And it's like the problems, they're not, it's frustrating because the concepts are not that hard. Right? It's frustrating because it's like, why is it so hard to have like two sets of sliding windows? There's something like, I feel like there's like a deficiency in my brain that's making it not easy to follow. But it's like when you get into the details, it is painful, right? Like I don't know if there is just like a nice way to handle, this case where you're trying to stride some things and it's like, these numbers have to be collected in here, and then this set needs to be collected here plus some more over here. It's just very strange. It's very strange. So I think it's doable to do something better than what we did. But I'm also happy with the idea that just limiting our options so that we can do an easier problem is great, right? This assert is saving us so much fucking pain. Like so much pain. Are you running a big OpenCL big array sum in anticipation of doing big map models? Yes, exactly. Exactly. And so yeah, I think if we just make our neural network so that our sizes are always like 1024. Oh, we should try, did we try strides that are like mega big? 1024 times 10 or something here. Fuck! I shouldn't have tried. I shouldn't have tried so we could pretend that it worked. Okay, I'll look at this one off stream. I need a break. But I'm sure it's close. I'm sure it's close. Thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 Pacific time to 4 o'clock Pacific time. It is 4:10 now. So if you're watching live, anywhere between 3.5 hours ago and now is when you should expect to see us live. We're working on this neural network thing, but there's a lot of other stuff in the archive. So if you want to check out what's in there, there's a YouTube link in the description, and we got a bunch of projects that you can kind of skim through. Some portion of these VODs go up on the YouTube there, and some portion does not. So today we were doing a bunch of reading on like trying to figure out how we're gonna do neural network architecture for our barcode scanner. So we were doing a lot of reading on like different CNNs and like, how they get to their final answers. So that type of stuff sometimes goes on Patreon or on YouTube member or in Twitch VODs, whichever place is most convenient. Please consider supporting. In return, you get the VODs that don't go on YouTube and the knowledge that this stream will live for some amount longer. This stream stops happening when I run out of money, and so every dollar I make doing this directly contributes, like the longevity of the thing. But anyways, that's all. Thanks for watching. YouTube, peace out, and Twitch, let's find someone to raid.